Hey everyone, today we're going to be talking about the fundamental theorem of calculus. The statement of the theorem goes as follows. If f is a continuous function on an interval a to b, and big F is the antiderivative of little f, then the integral of f of x from a to b is equal to big F evaluated at b minus big F evaluated at a. This theorem is essentially going to be a combination of two things, a combination of the definite integral and the indefinite integral where we're in search for antiderivatives. One of the major applications of this theorem in our context is that it completely solves the area problem for us, assuming that we are working with an integrable function f. Informally speaking, an integrable function f of x on a to b is simply a function whose integral from a to b exists. Let's also talk about some new notation. Putting capital F of x in brackets and giving a sub and superscript of a and b is just another way of writing the right-hand side of the fundamental theorem of calculus. Alternatively, one may write a vertical bar next to big F of x and sub and superscript it with an a and b. You get the same result. This is all known as evaluation notation. Thus, if I were to restate the fundamental theorem of calculus with this new notation, I would get that the integral of f of x from a to b is equal to the evaluation notation containing f of x and a and b. Essentially, this notation is just a shorthand for f of b minus f of a. It makes it clear what our integration bounds are going to be. So let's go ahead and look at some examples. For our first example, consider the integral of 3x squared times the square root of x cubed plus 1 from 1 to 3. Our first step will be to find the antiderivative of this function and then evaluate the antiderivative at 3 and 1. Now, the first thing I'll look at is the quantity underneath the radical, x cubed plus 1. When I take its derivative, I notice that I get 3x squared, which is my quantity on the left. This tells me that I should be thinking about the chain rule in reverse here. Next, I'll think about the antiderivative of the square root of x. The reason I'm considering the square root of x and not the square root of x cubed plus 1 is because I'm trying to break down this function composition so I can recognize this as a chain rule problem. Basically, I'm recognizing the square root of x cubed plus 1 as the square root of x composed with x cubed plus 1. So the antiderivative of the square root of x is the antiderivative of x to the 1/2, which will give me 2/3 x to the 3/2. This means that my antiderivative will be 2/3 x to the 3/2 composed with x cubed plus 1. Written out, I get 2/3 times the quantity x cubed plus 1 all raised to the 3/2 power. And then I use my evaluation notation and sub and superscript this with a 1 and a 3. If this notion with the chain rule is still a little bit weird, consider our antiderivative and take its derivative. We'll see that we get 3x squared times the square root of x cubed plus 1 as an answer. But now all that's left to do is calculate big F of 3 minus big F of 1. Putting this all together and simplifying gives us a final answer of 96.9. For our second example, we will take the integral of 4 times 3 to the x from 0 to 2. First, I'm going to factor out that 4, so that I'm looking at an integral rule that we already have. We have a rule that states what to do when I'm taking the integral of an exponential function with a base that is greater than 0 and not equal to 1. Since of course 3 is greater than 0 and not equal to 1, we get that 4 times the integral of 3 to the x from 0 to 2 equals 4 times 3 to the x divided by the natural log of 3 evaluated from 0 to 3. Since natural log of 3 is a constant, I can actually factor that out, which will end up giving us 4 over natural log of 3 times the quantity 3 squared minus 3 to the 0, which all simplifies to 32 over natural log of 3. In our next example, consider the integral of cosine of x from 0 to 2 pi. We already have the antiderivative of cosine of x, it's just sine of x. So I'm going to get sine of x evaluated from 0 to 2 pi, and by using the fundamental theorem of calculus, I end up getting an answer of 0. Which might seem a little bit odd. The reason this can be strange is because I'm computing an area and somehow I'm getting 0. When you consider the curve of cosine of x, we know that there's definitely space between the curve itself and the x-axis, but some of that space happens above the x-axis and some happens below. Basically what this means is my area above the x-axis is canceling out with the area below the x-axis. The areas above and below have the exact same value. Therefore, they end up canceling each other out. And that doesn't mean that the fundamental theorem of calculus failed us, but we would like a little bit more information because we do have area here that is currently not being computed. We know from trigonometry that cosine of x will intersect the x-axis at pi. In other words, from 0 to pi, cosine of x is positive, and from pi to 2 pi, cosine of x is negative, at least on the interval from 0 to 2. One can show the following, that the integral of cosine from 0 to pi is equal to 1, and that the integral of cosine from pi to 2 pi is equal to negative 1. In other words, pointing at our picture, the blue area is equal to 1, and the orange area is equal to negative 1. Now, we've seen examples of integrals before where I split my integral somewhere down the middle. The idea here is I'm taking my original integral of cosine from 0 to 2 pi, and I'm splitting it into the sum of two integrals, 0 to pi and pi to 2 pi. We know that this is a legal move, but this is actually a more enlightening step because now I have the values of the positive and negative areas. And naturally, if I add these two values together, 1 and negative 1, they cancel each other out, which is showing us our 0. In our next example, we'll consider the integral of the absolute value of e to the x minus 1 from negative 1 to 1. To understand the absolute value of e to the x minus 1, let's draw the graph of e to the x minus 1 without absolute values. Recall that taking the absolute value of a function simply just gives me all non-negative versions or all non-negative parts of that function. Here, if I look at e to the x minus 1 without absolute value bars, its function falls below the x-axis. In other words, it is taking on negative values. What the absolute value function is going to do for us is make our function strictly non-negative. In other words, it's going to take the left half of this function that is below the x-axis and essentially flip it upside down to make it positive. We can see this in the following picture. So now that we have the graph of the absolute value of x minus 1, we can recognize it as two parts. The part on the left that was originally negative got flipped upside down. So I can think of this as multiplying the original function e to the x minus 1 by a negative 1. This is giving me 1 minus e to the x. We know from algebra that scaling a function by negative 1 will flip the function vertically. Now in terms of the function that happened on the right-hand side, it was already positive, so we left it as it was, e to the x minus 1. So now that I understand what absolute value of e to the x minus 1 looks like, I can evaluate this integral more precisely. The strategy here will be to split my integral down the middle at the point where my function changes from positive to negative. Notice that in the original graph on the left, x equals 0 was this location where e to the x minus 1 went from being a negative function to a positive function. So I'm going to split my integral at the point 0. Paying attention to my integration bounds, this will give me two different parts. First, the integral of 1 minus e to the x from negative 1 to 0, plus the integral of e to the x minus 1 from 0 to 1. The hope is that the picture is going to clarify this breaking up process. 0 is this point where our original function, e to the x minus 1, was changing from negative to positive. To the left of 0, I was looking at 1 minus e to the x after this flip occurred, so that will be my new integrand from negative 1 to 0. And again, since e to the x minus 1 is already positive when it's to the right of 0, that integrand stays the same, and my bounds go from 0 to 1, 0 being this cutoff point. Now, using the fundamental theorem of calculus, I can go ahead and evaluate each of these integrals. After some algebra takes place, I get a final answer of negative 2 plus e to the minus 1 plus e, and we're done. The essence of looking at the absolute value of an integral essentially comes down to the following idea. Taking the absolute value of a function sometimes can construct for us a new function, or a set of new functions that get stitched together such that every piece of this function is going to be non-negative. Sometimes what this boils down to is looking at the parts of our function that are negative and just flipping them above the x-axis to force them to be non-negative. And again, how do you flip a function above the x-axis? Simply multiply it by negative 1.